Number 5 today, and today we are going to cover the last part of wet corrosion, which is passivity. It's a independent area of understanding, and after that we will summarize what we have learned in the wet corrosion, and that will be followed by the different types of corrosion. So let's try to finish the wet corrosion with the last topic of passivity. And passivity is something which is defined as some metals when they lose their reaction ability with the environment. Normally they react, but some of the elements lose their ability in certain environment. So that phenomenon is known as passivity. It is exhibited by the metals like iron, silicon, nickel, and many more elements, but not all the elements exhibit the concept of passivity. So this kind of phenomenon was first discovered by Faraday when he was making some experiment way back, almost 200 years back. So what he was doing was that he took a piece of iron and he put that into a dilute nitric acid, and he found that the piece of iron is corroding, which is shown in this schematic on the left. So what he did was that he thought maybe I should put the similar piece of iron in concentrated nitric acid and to see what goes on. And apparently when he put in the concentrated nitric acid, he expected to see even a faster rate of degradation, but that did not happen, and he found that the piece of iron is very stable with no reaction. And this leads to the discovery of passivity. So certain element in certain environment, like in this case iron in concentrated nitric acid, loses its reaction ability with the environment, which is the concentrated nitric acid, and this was defined as passivity. So he continued his experiment further, and he wanted to see that why this element is behaving like that. So he put the piece of iron initially in concentrated nitric acid where it stopped reacting with the nitric acid, and then he took the same piece of iron and placed them into another container containing dilute nitric acid, in which originally the piece of iron was corroding. But after the immersion from concentrated nitric acid, he found that again there is no corrosion. That means the environment of concentrated nitric acid is doing something to this piece of iron through which it is losing its reactivity. Now he wanted to find out whether this change is permanent or it is temporary. So again he took a piece of iron, similar piece of iron, put that in concentrated nitric acid, but this time he scratched the surface of the iron piece. After he scratched the surface of the iron piece, then he placed that piece into dilute nitric acid, and this time he saw that the material is interacting with the dilute nitric acid. So through that he established that whatever has happened, it is not permanent, it's a temporary thing, it's a surface phenomenon, and it can be destroyed. So the outcome of that, the passivity can be destroyed. But if he does not scratch the piece of iron, then he enters into this situation here, where a material will not react with the environment. So basically, from various oxide studies done, people established that passivity has to do something with the formation of certain oxide on the surface of metal. The exact mechanism is still not established, and it depends on metal to metal and alloy to alloy. So this kind of behavior can be very accurately established into the lab condition. What you need is a potentiostat, an electrolyte, and a piece of metal that you want to investigate. Now in this case, your oxidizing power or potential, so you can also represent this as a oxidizing power of the electrolyte. So as you increase the oxidizing power of the electrolyte along the y-axis in the lab condition, you see that the corrosion rate is increasing. So current density is proportional to corrosion rate or extent of corrosion or the speed of corrosion. So it is increasing and almost follow a linear path. It need not follow the linear path, but normally it follows the linear path. And then comes a level of the oxidizing power, which is somewhere here, that suddenly the material loses its corrosion ability and the current density now is established at a very, very low level or maybe at zero level. So this oxidizing power or potential is known as plate potential. So if you keep increasing the oxidizing power or the applied potential, you see that there's a vertical section here. That means your corrosion rate still remain at a very low rate. But if you keep increasing further, then there is a stage when it again start to show an increase in the rate of corrosion, and this zone is called as the transpassive zone. And the zone in which the material loses its ability to react is a passive zone. These zones can be easily established for all the metals and alloys in the lab with a high level of accuracy. So now whether your material is going to show this what we call as active passive behavior, because the initial zone is an active zone, then it enters into a passive zone, and then it enters into a transpassive zone. In the transpassive zone, the surface layer which gives the protections are completely destroyed. So the corrosion rate start to increase. So you can establish that because there can be now very different kind of environment. So if you are concerned that your material may show passive behavior or it not show passive behavior, so you can run the simple experiment, establish the data, and you will know how your material is going to behave. So basically, the initial understanding was that in case of passivation, some kind of protective layer is formed on the surface. Now this is almost similar to activation polarization. Remember, the word polarization is the slowing down of a reaction, which can be a cathodic reaction or it can be an anodic reaction, and that slowdown is because of the events happening at the either anode or cathode and electrolyte interface. So events happening at electrode and electrolyte interface. So basically, in the case of passivity, what you are doing, you have a metal and you have a solution here which want to react with this, and activation polarization is controlling the interfacial reaction. So with the passivation, you create a protective layer on the surface of your metal or component or whatever. So you are affecting the reaction that can possibly happen at electrode, electrolyte interface. So it's a special case of activation polarization. And this is very commonly exhibited by stainless steel, steels which contains certain levels of chromium and nickel, because in the presence of oxygen containing environment, 21% oxygen in our atmosphere, they make chromium oxide on the top of it. So if they make chromium oxide on the top of it, so the interface is controlled now. Now you have a chromium oxide which does not allow the oxygen or fresh water to go through. So the metal cannot go in the solution because chromium oxide is a protective oxide. So stainless steels show passivity in the oxygen containing environment. Oxygen and fresh water. So now if you recall the Faraday's experiment, the last set of the experiment that he made, he scratched the surface. He destroyed a part of the protective film by scratching it, a small area. So if you do anything to that surface layer, then you lose the passivity. And same thing is true for stainless steels also. So as I say here, it's self-healing in presence of oxygen. So that is a key word. Now, question, should you recommend the use of stainless steel in the deep sea application or in reducing conditions such as in the presence of carbonaceous gases commonly encountered in the power plants, power generation plants, especially where the fossil fuels are used, is full of carbon dioxide, carbon monoxide and all kind of things. So oxygen is always very limited there, especially the parts which carry the gases and everything. So do you think the stainless steel is a good material choice in the two areas, deep sea application and in the application where oxygen is not present or very limited, but you can have moisture, you can have other things in there. In deep sea you still have water, you still have chlorine. So in this situation, will you recommend? Will it be a good choice? Anyone can suggest me the answer? Stainless steel gets its name stainless because of the presence of chromium oxide layer, which is a protective oxide layer, and it is self-healing in the presence of oxygen, because the chromium from the stainless steel comes and reacts with oxygen to make chromium oxide. So my question is that, is it a good material choice in the deep sea application or in the application where the oxygen is extremely limited? Will you like to use this material? Yes or no? A common example is the use of these kind of steels in submarine application. Go inside the sea. What will you say? And when the submarine goes, it goes to the water, negotiate the structures in the sea, sometime rock, sometime plant, sometime animals, sometime it can be anything. The answer is no. Because if you're in the deep sea application, your oxygen is limited. Seawater contains 3.5% sodium chloride. Chlorine can damage the protective oxide layer. If the area is damaged, there is no oxygen to repair it. So that area is equivalent of active stainless steel if you look at your galvanic series. Remember, I pointed your attention towards active stainless steel and passive stainless steel, and the active stainless steel is the one which cannot form the chromium oxide layer, and the passive stainless steel is the one with the chromium oxide layer. And if you look at the galvanic series in your lecture notes, you see how different they are in the galvanic series. So now you have partly damaged area and you have totally covered area. So covered area will become anode or cathode? It will become cathode. And the destroyed area where the film is destroyed makes an anode. And there will be very significant corrosion. And same thing happens in a power plant, because again the oxygen is limited, so the oxide layer of chromium oxide cannot heal itself. It cannot react with oxygen. That's why all the structures that are put in the marine application, they don't put or they don't use the stainless steel where there's not enough flow of water. Because when there's not enough flow of water, there's not enough supply of oxygen through the water. So any damage that takes place cannot repair itself, and that leads to corrosion. So stainless steels are not used in those kind of conditions. So there are various theories which scientists use to explain the passivity. There's no global theory. Some people say that it's a formation of a very thin oxide film about 50 angstrom in thickness. Some people say that oxygen in the environment can absorb and then establish a chemical bond later on and make an oxide layer. And some people say that adsorbed or chemisorbed, or basically the similar mechanism. All the three mechanisms differ very marginally from each other, but all of them in common say that there is a formation of some kind of oxide layer. The mechanisms can be different because different materials have a different ability. So this film can be broken down as indicated by Faraday. So in modern application, the application of tensile stresses or impact of foreign objects, scratching can destroy this film. It's a surface phenomenon. And chemical action, like the presence of chlorine in the seawater, it is very aggressive. It can destroy chromium oxide locally. So to avoid the breakdown of the film, you can go for a better material selection. For example, if it's a steel, only for steel, SS stands for stainless steel. There are special steels which comes with this element molybdenum, abbreviated as MO, and these element addition increase the susceptibility, not increase the susceptibility, increase the quality of the oxide layer on the surface of the metal. Now, how it improves the quality or how it increases the resistance of the steel, that is very deep science. The other thing is that you can do the heat treatment and you can make your coating very homogeneous. You can even artificially create it. And any homogeneous coating will have a better corrosion characteristic. You can also design your material or the device so that there are minimizing or minimal tensile stress, and you can make it such a way that it is not like prone to people coming and scratching and all kind of things. So a lot of things you can do with the designing. You can also process the material in a way that the film that comes on the top of it, if it can be made amorphous kind of film, then it will be better, because many times, as indicated, the grain boundaries can also serve as a anodic side. So you can make amorphous. When I say amorphous, means there is no crystalline structure. That means no grain boundaries. Remember that grain boundary serves as an anode. So if you just remove the grain boundaries, definitely your corrosion resistance of the film will increase. So that is another way in which you can improve the surface characteristic of the material. You can make the coating better and delay the rate of corrosion or the extent of corrosion. All right. So that is all about the passivity. And that is the last topic of the wet corrosion. And up to this extent, we will cover it in the quiz 1. So we'll cover up to passivity or the end of wet corrosion. So very quickly in wet corrosion, we have learned that its principles are totally different from dry corrosion. The relative humidity value which demarcates the dry corrosion to wet corrosion is about 60 to 65% range. In Singapore condition, for example, because all of you are in Singapore, you must understand that average humidity levels are between 80 to 85%. So if you put anything outside, outdoor, you are exposing the material to not dry corrosion but the wet corrosion category. So two categories, dry corrosion category works in a different way, wet corrosion category works in a different way. So in the wet corrosion, the electrochemical reaction is very dominant, and we learned that it's a chemical reaction which accompanies the flow of electrons. So we try to understand this world here made of two parts. And we also learned that it has two parts, anodic and cathodic. And basically both the parts have to take place for the corrosion to take place. So it's very important. If one of the reaction stops, cathodic reaction stops, anodic reaction stops. If anodic reaction is stopped, then cathodic reaction automatically stops. So both of them are interdependent on each other. So this was explained with the example of corrosion of iron. So all this thing happened in first slide of the wet corrosion. Then we learned that what makes a anodic site and what makes a cathodic site. So various ways, if you connect two different type of metals, so one which is more reactive becomes an anode, and the less reactive becomes a cathode, and the corrosion is restricted to the material which is more reactive. So cathode will not corrode. So always remember, cathode does not corrode. Then we also see the situation which we encounter in the marine application, and we learned that the part of the, now we are not talking about two different metals, same metal, and the part which is exposed to the high oxygen concentration becomes a cathode, and less oxygen concentration becomes an anode. So the part which is exposed to the low oxygen concentration is the one which will corrode. Now it's the same metal here. Then we learned that in another situation in which you have the same metal, but one part is in the dilute solution, other part is in the concentrated solution. So we invoke the electrode potential values here, and with the example of iron, we saw that with low concentration solution, the electrode potential is more negative. If it is more negative, it becomes an anode. If it is relatively more positive, it becomes a cathode. Then we also learned about the variation of the stresses. Again, we have a same metal here in the variation in the stress also. So you have one pipe, you give it a bend and put it like this. So the bend area will have more stresses, and wherever you have whichever part, same metal again, more stresses, that area becomes anode, remaining area becomes cathode, and this stressed area is the one which is going to corrode. Then we learned about the metallurgical heterogeneities, and we saw that there are macro level defects and there are micro level defects. Macro defects included like scratches, pits, holes, cracks, and wherever you have this kind of surface inhomogeneity, you have the deficiency of oxygen, and that leads to the formation of anode, and the remaining area becomes cathode. Micro level, taking the example of steel and also the composites and all this thing, I indicated that all the materials have a structure that can be seen in a microscope. And under that situation, if your material has more than one type of phases, like ferrite and pearlite in case of steel, then these phases have their own chemical properties. If they have their own chemical properties, that means they will have different electrode potential. So once again, common principle, whoever shows more negative electrode potential becomes an anode, remaining area becomes cathode. Then we learned how to write anodic and cathodic reaction, and basically it is written in only one way, where the metal goes into the ionic form releasing electrons. For the cathodic reaction, there are about 5 types, and the first 3 types are most important, and that covers the acidic solution, basic and neutral solution. For basic and neutral solution, there is only one cathodic reaction. Reaction number 4 and 5 addresses the presence of contamination in the solution, which can be found in the artificial environment. Then we learned about what is electrode potential and how do we compute the potential of the cell, which is the cathodic potential minus the anodic potential, EC minus EA. And from that, we also learned that if EC minus EA is greater than 0, corrosion will take place. EC minus EA is less than 0, corrosion will not take place. So we took one example of copper immersed in the acidic solution without oxygen and with oxygen. Then we learned about EMF series, electromotive force series, and the galvanic series, which is for the corrosion susceptibility in the unpolluted seawater. So from that series, we learned how to interpret the series, how to choose the element, which elements are more cathodic, which elements are more anodic. So we learned that galvanic series is more comprehensive than EMF series, and both these series gives you the direction of the reaction. For example, if you combine iron with aluminum, it will make a galvanic cell, but which of the two metals will corrode? It will tell you that. How fast, how slow, it will not tell, but it will tell you that this will be the metal which will be corroding and this is the metal which will not be corroding. Then this electrode potential, can we compute the electrode potential if we don't have a standard condition such as concentration and temperature? If you change the temperature, many of the chemical activity don't take place at 25 degrees centigrade. Even the transmission of the petroleum takes place at about 60 to 70 degrees centigrade, or maybe higher. So under that situation, the potential or electrode potential will change. So in this situation, you can use the Nernst equation to compute it. Then we learned about the Porbig's diagram, which are the potential versus pH diagram, and that again tells you that given the condition in which your material is operating, you always have a plot between the potential and the pH, or oxidizing power and the pH of the solution. And if you know the potential, which you can find using a simple voltmeter by coupling it with a standard electrode, it can be easily found. You know exactly your material is falling in the corrosion zone, immunity zone, or the passivation zone. If it is falling in the corrosion zone, you know you have to make an intervention. Maybe you coat your material completely. If it is in the passivation zone, you know that your material have a tendency to make an oxide layer, but Porbig's diagram will not tell you it's a good or bad oxide. So you put in that situation, it will make an oxide, you check whether the oxide is good or not. And one very simple way to find it out is that if once it make oxide, do you see it's gaining or losing weight continuously or not? If its weight is stable after 1 or 2 or 3 days, that means the oxide is protective, otherwise it is not protective. And if the combination falls in the immunity zone, then you are well placed. There will not be any corrosion or anything. So that's the lessons we learned from the Porbig's diagram. Then we moved on to polarization, because from the EMF and galvanic series, we can tell that which materials combination, which material will corrode, which one will not corrode, what will be the direction, but we do not know how fast the reaction will go. Whenever we use the battery fades with time. So that explains why the fading takes place. Because as the corrosion proceeds, the ions are going in the solution. Some kind of oxide layers are forming. It's a natural occurrence. So once you have some kind of oxide layers are forming on the surface, your activation polarization kicks in. After that, concentration polarization kicks in. After that, resistance polarization kicks in. And apparently, the reactions start to slow down. So from corrosion perspective, it is good. But from the battery technology, it is not good. So you have to understand these 3 things from that perspective. Then we saw that the concept of course, the Evans diagram was quite simple. It tells you whether your system is anodically controlled. if the slope line is for the anodic reaction is more steep, or cathodic reaction control, or mix control, or resistance control. Then we came with a very important concept, which was exchange current density. Exchange current density helped us in understanding that the cathodic reaction on different metals can happen at a different rate. So it is a first indication that EMF series may not predict the rate of corrosion. And from that, the table, if you recall the table, you see the two examples that how the hydrogen evolution is different on aluminum and iron substrate. So higher the exchange current density, higher the rate of corrosion. Lower the exchange current density, lower is the wet corrosion. And that took us to the mixed potential theory. Mixed potential theory assumption is something which we have learnt in the wet corrosion to start with, but that means you have to follow them. And that indicated that in case of iron and zinc, for example, if we use the electrode potentials purely, then zinc is supposed to corrode more in the acidic situation, but actually it is iron which is corroding more in the acidic situation, and that's purely because the hydrogen reduction on the iron surface is much faster. So if the cathodic reaction is faster, anodic reaction becomes automatically faster. So in wet corrosion, it is the cathodic reaction which controls the overall rate of corrosion. This is the fundamental design principle in the wet corrosion. Minimize or eliminate the cathodic reaction. Anodic reaction will automatically stop. All right. So that is something which we learned, and we learned how to plot those diagrams of potential on the y-axis and current or current density on the x-axis. And finally, we also learned about the oxidizers, the effect of oxidizers, which you can also say contamination. And these are normally the high valency ions. And in those 5 cathodic reaction number 4 and 5 can serve the purpose of the contamination. So basically we learned that not all the contamination can be bad. There are 2 requirements for a contamination to work or to add on to the magnitude of cathodic reaction, and that was, first thing, it has to have a high potential and it has to have a reasonable exchange current density. So if it fulfills both these conditions, then it will increase the rate of corrosion. If it does not fulfill one of these 2 conditions, it will not increase the rate of wet corrosion. So that is something we learned from when the contamination will work and when it will not work. And finally, we learned passivity today, in which we learned that certain material in certain environment loses its chemical reactivity. The classical example, stainless steel in oxygen containing environment is quite stable. But any element that you inject in the environment which either inhibits the formation of this oxide layer or damages the oxide layer will destroy the passivity. So if you are invoking the principle of passive behavior of a material, you also have to ensure that environment in which you are putting it in does not have the destroying elements. Like normal traditional stainless steel, we cannot put in the marine application because the chlorine can damage the oxide layer and the corrosion can start there. So that is what basically in essence we learned from the concept of passivity. All right, so any question on the wet corrosion? And this is what we will cover in the quiz number 1. No questions? So once again, the quiz 1 will be held next week, 6:15 to 7:15 p.m. You still come at 6 o'clock because it will take us some time to distribute the question paper and everything. The questions will be like short questions. Some may be direct question from the lecture notes. Some will be indirect question, but invoking the principle of what you have learned. So just make sure that you read the lecture notes properly. If you have any doubts, you can come and see me. I'm sure the videos are available on IVLE, so you can always go through them also. If some part you are not able to understand, it will help you. All right, so we will not have any lecture or anything after the quiz, so it will be just 1 hour quiz. You people can give your papers, then you people can leave. All right, so next week will be purely devoted to quiz or quiz 1 only. All right, now let's move to the types of corrosion. So what you have learned so far is the corrosion can be divided into 2 categories, dry corrosion and wet corrosion. And in this part of the lecture, you are going to witness about 20 types of corrosion. And some of them can fit in the dry, some of them can fit only in the wet, and some of them can fit in both the dry and wet category of corrosion. So many times in the exam it asks identify the category of corrosion. So whenever we ask category of corrosion, you have to say either dry or wet. And if we say identify the type of corrosion, then you move into these types. All right. So keeping that in mind, let's see what are the different types of corrosion. Some of them we have already learned. So what you see in this slide is that there are the different types of corrosion, like oxidation corrosion, which can take place at the ambient temperature and the high temperature. And then we have sulfidation, halide attack, when metal and gases interact with each other. And this is mostly under the dry corrosion category. This is typically dry corrosion category. And then we have other types of corrosion which we have not seen so far, which is the general corrosion, localized corrosion, in which you have intergranule corrosion, pitting corrosion, crevice corrosion. A specialized type of crevice corrosion is the filiform corrosion. Then you have impingement corrosion, galvanic corrosion, and selective leaching. Then you have the corrosion in which you have mechanical stresses and the chemical environment plays almost equal part. And under that you learn about stress corrosion cracking, corrosion fatigue, and hydrogen damage. Then you will see the mechanical corrosion, in which the mechanical stresses are instrumental in damaging the material. In that you will see the wear, fretting, cavitation corrosion, and erosion corrosion. And then we'll move on to the biological corrosion, in which you'll see that how certain living organisms like plants or even insects can degrade the material over time. So you'll see the example of fouling and the degradation by ants. And in many places in the power lines, for example, even the rodents are the one who eats away the material. Remember the basic definition, the Latin definition of corrosion. Corrosion means eating away. So at time in the power lines and all these things, even the rodents can come and eat away the materials and all these things. So that is experienced by the people. Then we'll see the microbiological corrosion, which is seen in the underground pipeline, oil and gas industry, aerospace sector. So many examples will be taken from different sectors. So all these corrosion types will be covered one by one in the lecture. So let's move on. This slide is only for your reference. It's like a pictorial view how the different type of corrosion takes place. The uniform, galvanic when you have two metals. You have erosion when you have a slurry moving along the metal surface. You have fretting when you have some kind of vibration. It's a vibration induced corrosion. Then you have crevice corrosion when you have the crevices in the structure. speeding corrosion, certain materials in certain environment, exfoliation, when the materials come layer by layer. All of them I'm going to explain in bit more details. De-alloying, commonly used in the or seen in the marine application. Intergranular corrosion, commonly seen in the welded components, for example. Stress corrosion cracking, and in the cyclic loading you have corrosion fatigue. So these are some of the pictorial view for you to have some basic understanding. So none of this will be examinable. I'll not ask you to draw the pictures for this and all these things. So it's just for your reference only. All right, so we have already learned about the oxidation, corrosion, and the various metal gas interaction in the first part of the lecture under the dry corrosion category. So I'm not going to repeat that here. So that forms a first type of corrosion because we have about 21% of oxygen in the atmosphere. So oxidation corrosion is a dominating type of corrosion. The second type is the general or uniform corrosion. Now in this what happens is that if you look at the name, so you can define it, the corrosion which takes place uniformly over the material surface is a uniform corrosion. That's how you can define it if I ask you to define it. So since you can see this type of corrosion, it is quite predictable. You know exactly at what rate your material is being lost to the environment, and then you can take the preventive action at the right time. So it's quite safe. So what happens when a material or a component or a device is exposed to certain environment, slowly it starts reducing the thickness, and then at certain point of time it just loses its function. So if you have a structure like a rectangular structure, as the time progresses, the wall thickness will go down in this direction, and once it really thin down, it will just break apart. So that is the uniform corrosion. So the picture on the bottom shows like a hydraulic press exposed to a open atmospheric condition in a way that the room was not air conditioned. So you can expect a high level of humidity. And if you see that the corrosion is happening all over, so you can see the corrosion happening here, you can see corrosion happening here, you can see corrosion happening here, you can see the rust is here and everything is here. So when you see the corrosion happening all over the surface of your machinery, then it is classified as a uniform corrosion. Similarly, here is one more component. It is made of some kind of copper alloy. Mostly people use brass, and brass is nothing but copper plus zinc. So all these copper based materials show the green rust. You see, this is a green rust. So wherever you see green rust, you can assume that copper is likely the material which is being used in this application. So once again, you see the corrosion or the rust is present everywhere. It is here, it is here, it's practically all over the component. So this type of corrosion, if you're asked to identify this type of corrosion, it's a uniform corrosion. Here is another picture where the iron structure was used as a bridge. You can see a very thick sheet of steel here put on the two support column, which is shown here, but it was left unmonitored, and you can see that it is completely eaten away on the sides above this water body, and it just breaks down into that. So it's a typical picture shown by, if you go to the NASA website, you can see some of these pictures actually. So this is what happens, because they also train their scientists in corrosion. And here is a door handle assembly which we saw in the air conditioned corridor, not air conditioned corridor. It was not air conditioned when this happened. So what happened here is that, again you see the green rust here. And you see again the corrosion is happening on the handle, on the body here, practically wherever you see the corrosion is happening. So if someone asks you to identify this kind of corrosion, you can always say that the type is a uniform corrosion. So apparently the uniform corrosion takes place when your material selection is not correct based on the environment. Now if it's a corridor and if the humidity levels are high, if it's away from the rain and everything, you don't have to use an expensive element like copper based material here. It's a brass actually. So it's a copper based material. You can simply use stainless steel. It will work. Stainless steel will work and it's very cheap also. So the selection of proper material depending on the environmental condition is the first thing you should look for. You can also look for coating this structure. Even if you have already done that and you realize that you have used a wrong material, just paint it away. And once you put some paint, it gives a barrier, activates the activation polarization, and your corrosion will stop. So use of coating is other way. And if your structure is quite big, like it happens in the marine condition, that at times you don't have a choice but to use a material which will corrode if you don't make an intervention, then you can use a cathodic protection, which I will explain in detail. That is nothing but attaching a more reactive element to that structure. So invoking the galvanic corrosion principle. So once you attach a more reactive matter, this area or whatever you are trying to protect, even this guy, it becomes cathode. And you just weld a piece of, say, if it is brass, you attach a piece of zinc to that, it will work. It will stop the corrosion. So these are certain ways in which you can minimize uniform corrosion. All right, straightforward. Let's move on. Localized corrosion. So the first type we have seen is the corrosion that takes place all over the surface of the material. Now we are addressing the corrosion which takes place only at selected location over the whole structure. So it's more challenging. It may escape your attention. And if it escapes your attention, the failure can take place right at that point, at that location. It can be a structural failure. That is what we are going to learn in the localized corrosion and their impact. The first type is intergranular corrosion. How do we read this word? Granular means grain. Inter means along. So the corrosion that takes place along the grain boundary is called as intergranular corrosion. This is how you will define it if someone asks you in an interview or exam or somewhere, what is intergranular corrosion? The corrosion that takes place along the grain boundary. Commonly seen in stainless steels, and you know stainless steels are quite widely used in infrastructure applications, quite widely used. So what happens is that if you weld, whenever you make anything, even a bus or a cycle or anything, you end up putting rivets or you end up welding that thing actually. So you cannot avoid welding in many engineering applications. So if you're not careful with the type of the material and all these things, so in this picture what you see, this is a weld here. This is a weld here. And if the welding is not done properly or if the material is not chosen properly, then you see this intergranular corrosion happening at a certain location from where the welding is done. Now, how it takes place, why it takes place is what we'll see soon. So to be very clear about the concept of intergranular, because there's another word which material scientists use is transgranular. So it's good to understand the difference between them. Inter means along the grain boundary. So this is, for example, grain number 1 here. And you see that the damage is going along the grain boundaries of different grains, and that's how the material failed. But when we use the word transgranular, that means the damage goes through the grain, not through the grain boundary, through the grain. So that is the difference between transgranular and intergranular. So in case, I don't want you to get confused when you see this transgranular word also. Trans means across, inter means along the grain boundaries. So trans means across. and inter means along. So that is the basic difference between the two terms. They are different. All right, so let's try to see what's happening here. Now, as I say that every material has a microstructure and every material is made of grains. So this, if you look into the optical microscope, you'll see some grains. So these all grains and these black lines are the grain boundary. Now, in case of stainless steel, because we have chromium and we have nickel and we have carbon. So they are the three prime elements which are present in iron to make it a stainless steel. So iron is the main element, plus chromium is second one, nickel is third one, and carbon is present in the small quantities. So what happens after we do the welding, then these precipitates, or the second phase, which is Cr23C6, are formed at the grain boundaries. So you see this black round thing, these are the chromium carbide precipitates here. So if you blow up one grain boundary zone, you see that this black line is a grain boundary and this black are the chromium carbide precipitates, Cr23C6. So basically, when the chromium carbide precipitates are formed as a result of welding, because we take it to a high temperature and cool it down, so this phase comes out. So this chromium and carbon is taken from the zone which is next to the grain boundary, and as a result of that, this area around the grain boundary gets depleted in chromium. So it makes a chromium depleted zone. And if you go away from this zone, you again have the same amount of chromium, which is good enough to give you chromium oxide, protective layer. Right? So basically, I think it is in your lecture notes, is the chromium depleted zone, because it does not have a protective chromium oxide left now, so it will make an anode. It's more like a, if you recall your galvanic series, active stainless steel. And the chromium rich zone, which has chromium oxide, will serve as a cathode. And it acts as a passive stainless steel. So the corrosion will take place along the grain boundaries, because that area is not protected. Is it clear? So this is intergranular corrosion. So if you look at, for example, this galvanic series here, you see the passive stainless steel, which contains chromium oxide, and active stainless steel, no chromium oxide. And this is exactly what is happening here. So you have a small area without protection, remaining area with protection. Since the cathodic area here is big, the corrosion happens very fast. Because no matter how much iron dissolves in the grain boundary, it is always supported by a cathodic reaction. So this is intergranular corrosion. So before we saw that, see that picture, this one, which shows how the microstructure looks like. You see this black area? Here the grains have fallen off as a result of intergranular corrosion, because there is no bonding left between the grains now. All the corrosion has taken place along the grain boundary, and the grains start falling off. And slowly it will convert into voids, and voids under the application of stress, your material will fail. So this is intergranular corrosion. So grains are not there anymore. All right, so let's go back to this one. So we know that this intergranular corrosion takes place because of the precipitation of this one, and since this phase comes out, it leads to the situation of formation of anode and cathode. So the culprit is this phase. So now, if I can do something with the phase, if I put it back into the solution, I can avoid the internal corrosion. So I can heat treat it. I can take the steel back to high temperature where this phase dissolves and no depleted zone, no rich zone, and there is no internal corrosion. The second option, if you look at the slide, 2 slides beyond that, I can put some elements like titanium or columbium in there, which will make carbides. So they will react with carbon and not chromium based on thermodynamics. So if the chromium is in the solution, it is the one which gives me the chromium oxide layer, and hence again you can avoid the intergranular corrosion. The third way I can handle this situation is I create a steel with very low amount of carbon so that it does not react at all. It's so less that it cannot really react with the elements, and these type of steels are called as steels with a capital L, like 304L, and the carbon has to be less than 0.03% in the steel. So you can weld these steels nicely, it will not fail by intergranular corrosion. So there are 3 ways in which I can handle intergranular corrosion. All right, so that is about the internal corrosion. So we take a break now. It's almost 7 o'clock, and we'll try to understand this more by using this case study from the industry. All right, so we start again at about 7:18 to 7:20 zone. I guess all of you are here. 20 minutes are over. 7:19 to be sharp, and we can start with this case study. Now, this is not a hypothetical situation, it's a real case study, so it's not like fiction here. Now, what is happening in this situation is that there was a company who was based in USA with an expertise in installing condensers, and they put some of these units into a neighboring country here, and there was failure in the condenser. And the failure was in the welded area. So the company who was using these condensers assembly, they suspected that the failure was mainly as a result of intergranular corrosion due to the bad material. So essentially, they did not say that your condenser is bad or something like that. They say it failed, and it failed because of intergranular corrosion, and the material that you have used in the condenser is a bad material, so we want our money back. So it was a few $1 million lawsuit that they put in there. And so the company here, which was based in Singapore, who was acting on behalf of the parent company, they did the composition analysis. They used the steel 316, it's a stainless steel. They checked the composition, and they found that the composition was in accordance. But since it was a court case, so they have to take the advice from the expert to validate their point that the failure might have occurred because of other reasons, but not the internal corrosion. So in a way, the company which was using these condensers, they made one fatal mistake. They said that the failure was because of intergranular corrosion. So that means what the parent company has to do is that, is it internal corrosion? If yes, they lose a suit. If they say, if it is not, the failure is not because of internal corrosion, they win the suit. So it was a very simple problem. So some of the sample came after they have done the composition analysis. Then some of the sample came to us, and we did and the samples were sent by the company who experienced the failure. So apparently they were the one who chose the sample and sent to us. So we took the samples and we polished it and we put in a scanning electron microscope so that we can see it more clearly after giving some kind of preparation technique. And what you can see here are a hybrid picture. This picture can be divided into two parts, the one on the left side and one on the right side. In the left side, you see the structure of a material that's seen at higher magnification, and apparently this magnification is 3500 times. 3500 times. So what you see here is a wide grain boundaries. You can see that. So this is grain number 1, for example. This is say grain number 2. This is say grain number 3. This is grain number 4, and this is grain number 5. So this scanning electron microscope comes with a scanning ability in which they can also read the composition of an element in the area that it is seeing. For example, this is the area that microscope is seeing here. I cover that into the red box. So the electron beam will go line by line, and cover the whole area and show what element is present. So we wanted to do the mapping of CR. CR stands for chromium. Because chromium is an element which gives chromium oxide, and chromium oxide is a protective oxide. So we want to see how the chromium distribution is across this whole area, which includes the grain and which includes the grain boundary. So what you see on the right side of the picture is the white dots. So whenever the electron beam reads a chromium signal, it gives a white dot. If it doesn't read it, it gives a black dot, okay, or the black area. So basically this shows that you have the chromium present reasonably uniformly all across this area which is on the left hand side. Then we took the same picture and we blew up the magnification even more, and now what we see is, again it's a hybrid image. This is a structure of the metal at the high magnification. So this magnification was 7500 times, almost double. And this is the grain boundary shown by the diagonal red line. So this is the grain boundary. And the picture on the right hand side here shows the chromium mapping. CR stands for chromium. So you see that the chromium, that white dots represent the presence of chromium, and which is reasonably uniformly distributed in this area, which is shown on the left side of the hybrid image. Now based on these two evidence, can you comment whether this failure was indeed because of intergranular corrosion or not because of intergranular corrosion? So take about 3 to 4 minutes, refer to the lecture note, discuss with your colleagues, and then I will ask you to raise hands for a possible solution. Remember that this suit was a multi-million-dollar suit, and I'm talking of almost 15 years back this case came in. So that time it was quite a lot of money. Even a few $1,000,000 now is quite a lot of money even now. So is this case a typical failure case because of intergranular corrosion or not, based on the evidence that you are seeing in the micrographs? Please refer to your lecture notes, talk with your friends, and discuss. left, 7:30. I'll ask you if anyone has already cracked this thing or not. If anyone has cracked it, you can raise your hand. Let's see what you have to say. Anyone thinks it's an internal corrosion failure or it is not an internal corrosion failure? You have only two choices. 50% probability you may be right. Anyone want to make an attempt? Anyone practically? You can expect this kind of questions in quiz 2. Yeah. Okay, that's a correct answer. It is not an internal corrosion failure. The reason? Absolutely correct. That's it. 2-sentence answer. Saved $1 million for the company based in this thing. 1 day job for us to make the samples, polish, get the picture. We earn about $4,000 out of that. But company saved $1 million, millions of dollars. The fundamental of internal corrosion is that if it is indeed a case of internal corrosion, as he has rightly said, where are the precipitates? So precipitates are missing, and there is no chromium. So there has to be a chromium depleted zone here, if you recall that picture which I explained to you. So that means you should have a zone here in which you don't see any white spots, or their intensity will be extremely limited. So we don't see those two features, which is a telltale sign of internal corrosion. So it is not internal corrosion. The report was sent to the court, approved immediately. Is it clear to everyone? Anyone has a differing opinion? All right, so this case is clear. So we move on. Pitting corrosion. Again, we are talking of the localized corrosion. Pitting corrosion is, why it is called pitting? Pit. Pit means hole. So basically, you have a structure and you have some hole made. Now, to understand the gravity of the situation and why this kind of corrosion is called insidious in nature. You know, many times the chemicals, gases, oils are transported from one place to other places through pipes, underground pipes or overground pipe. It really doesn't matter. You have, say, 10-kilometer long pipe. And in one small location, you have a 1 millimeter pit formed. So the whole piping system fails because of one small pit, a few millimeter in diameter. So the whole system fails. And that is the gravity of situation, that is small. So whole of the pipe you can see bright shining pipe, and one area is corroding, pits form, liquids start leaking off, the whole system has to shut down. So that is the concept and the gravity of pitting corrosion. That's why this is not a type of corrosion we expect to see anywhere. And especially if you have more compact units like condensers and all this thing, where it is carrying hot liquids and cold liquids, the chemicals of a different type which may be incompatible, and if there are holes formed in these pipes because of the pitting corrosion, you can have the mixing of chemicals and potential explosions. So pitting corrosion is a type of corrosion which is very dangerous in nature. It's not easy to inspect, but there are a lot of science developed to tackle pitting corrosion. So if the material is susceptible to the pitting corrosion, we have to ensure that we take proper preventive measures. So typical combination which lead to the pitting corrosion are like stainless steel. Always remember, iron based material including stainless steel are most commonly used material in many applications. So in acidic and chloride, if your environment is acidic which contains chlorides and you have iron based material like stainless steel, then you can expect pitting corrosion to take place. So do not combine them. So basically these material mostly which shows the pitting corrosion are the one which shows the passivity phenomenon. Now let's try to understand this point number 2. You have a stainless steel pipe, for example, long pipe, and it is covered by chromium oxide, so it is giving the protection, but for various reasons you put a solution unknowingly, acidic chloride, it says stainless steel is stainless, doesn't matter, but this chlorine damages the passive layer, so now you have a small pit formed here. This is anode because the protection is gone. And you have miles and kilometer long cathode here. So no matter how fast the anode or that pit dissolves, it is always supported by the cathodic reaction because cathodic area is so big. So immediately the pit will cross through the thickness of the wall and the system will fail. Now the pits appear as some kind of a circular appearance on this thing, so it shows another piece here where the piece is welded and you see these black holes here. These are all pits. So you can see them with your eyes, but question is where to see them. That is the problem. Here is another part of stainless steel with lot of pitting in there. After removal you see the black holes are there. They need not be exactly circular, but somewhere there, elliptical also. Copper pipe carrying drinking water. Potable is, it means drinking water, something which you can ingest. And you see that the big pipe, but you have a small area which is undergoing pitting corrosion. And apparently it failed because of the pit becomes deeper and deeper and it collapsed. Now what happens is, if you are transporting some liquid at no pressure, normally you have to apply pressure to transport, but if you are transporting in a way that no pressure is required, then maybe the pipe will not burst. But if the pressure is involved in the transmission, then these holes may become a site of stress concentration and you can have a pipe burst. Another picture under microscope is, I think, roughly about 100 times magnification, looking at the micron bar here, and you see these black holes here. These are all pits. So any material that shows the presence of pits, either visually or under a slightly high magnification, that is a telltale sign that this material is failing by the pitting corrosion. That indicates that the material and environment condition is not proper and we should avoid that. Another picture which shows the presence of holes randomly distributed, and sometime what happens is that the small pits are formed and they form closer, then they start merging with each other, and then from say 1 millimeter they becomes more and more, and that aggravates the situation. So if you think about it, if you take a cross section and your pit is going here, and this is a thickness, for example, this is a thickness of pipe T. So once the thickness is compromised beyond certain extent, your pipe opens up. So that is kind of damage we have seen. So you can have the different shape of the pits, and this is not for your memorization, it is only for your information. So I'm not going to like test you that draw 5 different type of pits, not really. It is just to show that these holes which are made can have the different morphology like narrow, elliptical, wide, undercutting, subsurface, this kind of thing and all this thing. It all comes under the different environmental situation. So here shows a busted pipe, split tubing, because the hole has made, so the liquid is under pressure, so you can have the split tubing like that. And as a picture I draw that once the pitting comes in, and this is the thickness of the wall or the pipe, and it has compromised almost like 60 to 70%. And this is a situation when it leads to this kind of thing. The tubing can split open. This is another case where the pit is formed here. So after you remove the paint, you can see this pitted area is here. So which is more of a concern in the pipeline industry, because you have walls and the thickness of the wall cannot be compromised beyond certain extent. There's always factor of safety, so you can always compromise them, but not beyond certain extent. So essentially, the surface, either visually or under the high magnification, you will see some kind of a small holes, elliptical, circular, and whatsoever. And these are the pits, which is typically revealed by a material which is undergoing pitting corrosion. So what happens, how the pit is started is that because maybe your surface is crashed, maybe there's an inclusion which is very active, or active means anodic, or maybe there is a surface compositional inhomogeneity which can lead to the formation of a anodic site. So once this anodic site is formed on the surface, which is anodic site, and you know that at anodic site metal will go into solution releasing electrons. So the damage is only in this area, but the remaining area is okay. And in the atmosphere, in the normal condition, you have oxygen, you have water. So it will undergo the cathodic reaction, which is oxygen plus water plus electron to give OH minus ions. And now again you have a very big cathode. The pit is anode, very small, 1 to 2 mm to start with, and you have a very big cathode. And the reaction proceeds very, very fast. Very, very fast. So how fast is this reaction? For example, if you have a uniform corrosion and your surface is getting slowly eaten away, so uniform corrosion, then the rate of dissolution is about 10 to the minus 13 meter per second. And when a material is going through a pitting corrosion, that means your thickness is compromised at a rate of 10 to the minus 7 meter per second. That's a 6 order of magnitude difference. So that means your corrosion at that local area is moving at 6 order of magnitude faster. How does it translate to the life of a component now? If you put a pipeline for 20 years, it can fail within less than 1 year by pitting corrosion. That is a 6 order of magnitude faster. So think about it. You have an underground pipeline. You laid it down by putting a lot of money for 20 years. It fails within 1 year time. How much loss it is, plus plant shutdown and all this thing. So that is the gravity of pitting corrosion. So how do you prevent it? Whenever there is a material which is undergoing pitting corrosion, it exerts a potential which is called as a pitting potential. This potential is available in many handbooks and textbooks. So if you put a artificial electrical system and put the voltage of the system lower than the pitting potential, then it will not go through the pitting corrosion. That is one way. So for any critical application, you can adopt this measure. These values are available in the handbooks. Number two, you can increase the inherent characteristics of a material towards corrosion, and molybdenum is a magic element. If you recall, this is an element which improves the corrosion resistance of stainless steel even in the seawater situation. So here is, it also improves the resistance of the steel even against the pitting corrosion. And material selection. Material selection, for example, you will see this kind of graphs which are available. If you do some simple literature search, you can easily find it. So this is, if you see that on the y-axis is the temperature in degree centigrade, and x-axis is the amount of chlorine in the solution, and this is a typical 304 stainless steel. So how do we read this graph is that below this solid line 1, if you have the temperature versus chlorine concentration below this solid line, pitting corrosion will not take place, no pitting. And if you have the temperature versus chlorine concentration above this solid line, then your pitting will take place. So we can switch from 304 stainless steel to 316 stainless steel. So now this window where there will not be any pitting corrosion is increased by this magnitude. That means we can operate our material at higher temperature and higher chlorine concentration. And if we go to another more specialized steel, say CS2205, then we have a very big window below which pitting will not take place. So material selection. So once again, this graph is not for you to memorize, it is for you to understand the role of material selection and the choices that we have with us. And where to look into it is simple handbooks or Google search, and you will get the answer. And at time, all this information is in the company manuals that you are working in your kind of application. So this information is there. Again, some pictures to show how the black pits shows up on the surface. Again, another picture which shows the black areas here, typically indicative of pitting corrosion. So this helps you in identifying the type of corrosion. If you understand what is pitting corrosion, if you can look at the surface and tell that, oh, this type of corrosion is pitting corrosion, so you exactly know. Go to a book, see how do I prevent pitting corrosion. Look at your material, look at the environmental condition that your material is subjected to depending on the type of industry you are working in, and you can easily find a solution. 90% of the cases you can find solution from the literature at this point of time. Only 5 to 10% cases are like that, in which you have to do more extensive search. At time you may have to do some experiment, but those are only in 5% category. All right, so let's move on to the crevice corrosion now. Crevice, what is the meaning of crevice in English? The meaning of crevice in English is gap. So whenever you have a situation where there is a gap in the system and there is a stagnant water or some kind of liquid solution, you have crevice corrosion. Many of the components, if you look at this, they are fitted with each other, they are welded with each other, they are bolted with each other and all these things. If you don't do those things properly, there will be gaps left. And whenever there is a gap left, and whenever there is a stagnant solution or the humidity levels are high or it rains in that area frequently, you can encounter crevice type of corrosion. So crevice corrosion is a corrosion in the gaps. That's how you can define it. Now, for example, whenever you bolt a structure and you put a threaded screw or whatever, you always have some gaps formed in there. And that is where you will have the corrosion takes place because this area becomes anode in the cap because of the low oxygen concentration. Oxygen cannot diffuse in very easily. With respect to the part which is exposed to open atmospheric condition, which will form a cathode. Similarly, if you have deposits on the surface of a metal, then the interface between the deposit and the metal is again depleted in oxygen and becomes an anode. So you will have the corrosion happening below the deposit. So that's why at time crevice corrosion is also known as under deposit corrosion. Under deposit corrosion. So two reasons here. So what happens is you have a situation in which your two parts are not fitting well with each other, or they are not bolted each other very properly. And you know that all materials corrode under the wet atmospheric condition. So now you have a situation that you have a wet condition, you have a gap there, and water can condense in there, and apparently over the time the corrosion will take place over the surface. Very soon the gap will be devoid of oxygen. So now it will depend on the oxygen to come and diffuse from outside, which will be always a slow process. So wherever there is a gap, deep-seated gap, so a reduction in the oxygen concentration, if you recall, what makes an anodic site and what makes a cathodic site in the marine atmosphere. So low oxygen concentration always promote the anodic site, or the site which corrodes. So then the corrosion starts in the crevice area. It propagates. What will happen if it eats away? Corrosion is eating away of the material. What happens if you bolt a structure so that it's tight, and inside where the tightness is there because of the threads and everything, and that area is eaten away, so it will loosen up with time and it will break apart with time. So that is crevice corrosion. A typical example is like this one is taken in block E3A. This door opens outside to the environment, and what you see here is a lock, and this is probably because shining white, so I assume it is stainless steel here. And you know that in Singapore it rains often. Even in the non-rainy period, once in a week you can expect some showers. So you see there's still quite white bright, so no signs of corrosion. It's quite all right. But if you look at this area here, which locks in, so there's a cavity inside here in this part. So cavities where this part shown here goes inside when it's in the lock situation, and you see how much it is corroding. And since the rust is brown, so it's a steel. So now you have a situation, you have this outside part of the handle which is not corroding in the same atmospheric condition, and the part which goes into this cavity is here, cavity number 1 here and cavity number 2 here inside, that is corroding because it remains locked overnight every day. So for 12 hours it is locked at least. Because when it goes inside, it forms a crevice. And forms a crevice, that area is depleted in oxygen. And when it's depleted in oxygen, so inside it starts to corrode. Outside becomes cathode, it does not corrode. Cathode never corrodes. So now you have a part of that which is corroding here. This is a typical example of crevice corrosion. And if you have the chlorine in the atmosphere, it has a scavenging effect, and which can take away the metal ions, because once the corrosion takes place, metal goes in the solution form. So this chlorine is the one which goes inside the crevice, bring out the metal ion and creates more space for the corrosion to take place. So it aggravates the crevice corrosion. Another example, this is a traffic guide post. Traffic guide post. in front of the, it used to be in the main front of the main library. You know, the new building, previously there was a car park, and at times they used to block the car park, and by doing that they just put this kind of thing over. There are 2 or 3 of that thing there, so they can block the whole road just by putting this guidepost there. So now you see this guidepost very closely. You see this is a part which goes into this cavity here. And obviously in this thing the water can accumulate. So you see the part which goes into the cavity is the one which is corroding, not the one on the top of it. So this is another example of crevice corrosion. So how you can prevent this kind of corrosion? Improve the structural design. Instead of bolted structure, use a welded joint. No gaps, no crevice corrosion. You can design the vessels which store liquids for complete drainage, because if you do not design them for complete drainage, then you have a stagnant water situation. So remember, the crevice corrosion is the gap plus stagnant water situation. So that will promote crevice corrosion. By preventing debris from resting on the metal surface, because when the debris are formed on the metal surface, under the debris is the anodic area deprived in oxygen, so it will lead to the crevice corrosion. Non-absorbent gasket. If you have seen the plumbers working in your house and fitting something, fixing, screwing something, bolting something, or whatever it is, they always use a white tape. Why do they use a white tape? It's just to seal the gap which will otherwise be formed because of the presence of thread. And by that, he increases the life and minimize the crevice corrosion. So that Teflon tape is done to minimize crevice corrosion. Allowing to always go for better material. And inhibitors are some substances which you can add. If it's a closed system, you can add some elements which gives a protective layer over the whole exposed surface. So you learn about inhibitor later on under the corrosion prevention. So another way to minimize the corrosion. So let's try to look at a case study, a situation which was experienced by a typical car company way back in early 1980s. So they designed the car door in a way that the design is shown here in this picture here. So when it rains, this rainwater used to seep through this glass panel, part of it goes down, and the bottom part of the design of the door was like this, which is shown in the blown up view here. So you have a stagnant water situation here, and then you have more oxygen here, and as you go inside here, there's a depletion of oxygen. So basically, the holes used to form at this location. Because remember, when you raise the glass of the window and put it down, it goes inside. So there's always some gap in which the water can go and seep inside. And this was the design. And the holes are formed, so when you're driving a car, then the air used to go from these holes to the person who is driving the car. Of course, if you're in Singapore, it doesn't matter because the temperature is 28 degrees centigrade. But if you are in the cold countries, like Canada, then what happens? At times you have minus 10 degrees centigrade jet of cold air coming and hitting your lap. It can freeze you. So you're compromising with the safety of the passengers in the car. So based on this information, what kind of corrosion is this one? Why this corrosion is taking place? What type of corrosion is this, which is happening at a certain location? So remember, it's not happening all over the car door. It's happening at certain locations. So is it a uniform corrosion or a localized corrosion? So that is the first test, uniform or localized. It is localized because the holes are formed at certain location. Okay? It's not happening all over, so it's a localized. So under the localized, which corrosion you have learned so far and which one fits into this one? Interground corrosion, pitting corrosion or crevice corrosion? It's a crevice corrosion because now you see the crevice corrosion needs a gap which is here and stagnant water situation which is because of the bad design at the bottom of the door, right? All right. So next question. How can you prevent this type of corrosion? What can you do? If you understand what type of corrosion is this, the next stage is why this corrosion, what lead to that corrosion? Factors. You kill one of the factor and you kill the corrosion. Am I right? So how do you kill one of the two factors of crevice corrosion? A gap and a stagnant solution. What you can easily handle here? The whole situation is given to you where the water is accumulating and all these things. So what will you do? That time the car recall was not common, all right? We're talking of almost how many years back? 30 years back? 35 years back? So what can you do here to kill this type of corrosion? And people found the way, very simple ways to do that. Hardly cost them a few tens of dollars to fix it without getting it replaced, complete doors and everything. So can you think of anything? Say take 2 minutes. So we have already identified the corrosion to be the crevice corrosion. Can you control the rain? We cannot control the rain. It has to happen sometime or other. It has to go in. So what can we control? Go to stage 2. What can we control here now? Yeah. You raise your hand, right? No. Okay. All right. Give it a try. Give it a try. You want to try? Yeah, please. Yeah, see, here's the experience. Already talking about kill the gap. That's the basic solution. So what people did was that, I'm talking about 35 years back, so don't compare this technology at this point of time with more than 30 years back. So what they did was that they just closed this gap by injecting wax. You can use a silicone rubber. And once the gaps are gone, no stagnant solution. So with this kind of profile, what you are doing is that, of course you cannot control the rain. If it has to rain in Singapore, you can't stop the rain, right? So this rain has to come and then immediately drained off through the drain hole. So it was a bad design. So by injecting the wax, they give a slope like that so that all the water that comes in goes to the drain hole straight away. No stagnant water. One of the condition of the crevice corrosion is killed. Crevice is gone. So no crevice corrosion. Problem solved. So sometime you may feel that it's a difficult situation, but actually it's not. Question is, do you understand the concept of that type of corrosion? You can easily find the solution. Right? Another situation, Singapore, maybe about 5-10 years back now, 2006. A boy and a girl were found dead in the car in a car parking lot. Engine was running. The rear bumper was modified. So when it is modified, the exhaust gas did not escape in this direction. The car was parked. It was not moving. Okay. So this exhaust gas took a detour, go inside, and on the floorboard there were about 4 or 5 holes on the floorboard. So this gas came and went inside. And the carbon monoxide, which is one of the gas which is released, does not have any odor. That means you cannot smell it. And it is toxic. And both these people died in the car. This can happen in the situation when there is a traffic jams. And if you are in an air-conditioned car, it can happen because there are a lot of cars in front of you, in back of you, you cannot move, you are static. All right. So what really happened? This was a 13-year-old car. And the floorboard had some holes. The size of the hole was equivalent of 10-cent coin. 10-cent coin. Just visualize the size of a 10-cent coin, something like maybe this one size, maybe a bit bigger, like this. 4. That was good enough to kill these 2 people. So this case was highlighted actually because it was quite unusual case. So it came in the newspaper also and all these things. So immediately the reporter went to the car specialist and say what happened. So they say that, you know, they should bring the car for regular maintenance, and especially if it's 10-year-old, then we should do that. So some people say that, oh, we have the cars with the galvanized parts. You know, the galvanized, same steel plus zinc coating, right? So the term galvanizing is very common, used practically many places. So they say that, you know, like when you drive a car, you have sometimes pebbles, you have dust, you have this and that, and all these things. So they can come and damage this part, this coating layer. You can have some cracks in here, and that lead to the corrosion, which is not correct. So don't take this news and opinion of the people because they are not corrosion experts actually. Because even if there's a crack, as long as the zinc is there, it will protect the base metal. Okay. And if there's a crack and the damage is because of the crack, so you will not get holes, you will get cracked areas. So that statement is wrong. So what kind of corrosion you think is there or experienced which led to the formation of holes over the time of 13 years? What type of corrosion you expect to have happened on the floorboard of this vehicle? Let's analyze from a corrosion point of view. All right, take 2 or 3 minutes, work on it, then what caused it and what can we do? What we have learned from this thing, how to manage the crevice corrosion. So do you think it's a case of crevice corrosion? Obviously I'm in the crevice corrosion, so it's a case of crevice corrosion, so I gave you that answer. And now you tell me why I'm saying it's a case of crevice corrosion. Think about it. The penetration of the gas from outside to inside. I don't see you guys interacting with each other. It's very important. You go in a company, you have to work with your friends and colleagues and the lecture notes. It's very important. That's how you learn. You cannot be isolated. Show the teamwork. And you will not get this on internet also. So don't Google search. All right, one more minute and then we will try to discuss it out. Okay, who has answered? Anyone want to give it a try? I've already answered you that this type of corrosion is a crevice corrosion. So how it is a crevice corrosion? That is my next question. So for that you have to understand what causes crevice corrosion. What are the situations which can cause crevice corrosion? So what you could possibly imagine happening at the floorboard of a car? And this can happen in Singapore, any place which rains. It can happen in all the cold countries. It can happen in many, many places in the whole world. Anyone want to try, or I give you the answer? Anyone want to raise hand? Anywhere? No? All right. What you expect at the floorboard is that mud deposits. Remember, the crevice corrosion is also known as under deposit corrosion. Whenever the mud deposit in the underboard, there's always a gap. It's not a chemical bond. It's not a welded zone. And that gap becomes anodic over time and start to corrode. And over the time, the corrosion will proceed and the floorboard will be corroded. So that is the main reason what led to this formation of holes. Remedial measures, maintenance. Maintenance is the best remedial measure for under deposit corrosion. Now what happens, for example, in the Singapore Defense Forces, when you have these vehicles, amphibious vehicles which goes in the sea and comes out of the sea. Amphibious means you can run on the land, you can run in the sea also. So when they used to come out from the sea, it used to come with the salt deposits. And initially when the understanding was not there, it used to come out, parked into the closed space, and they start to see corrosion happening under these deposits. So they realize it and they start to maintain it. So now they use the high pressure water jets to just clean the vehicle. If you use the high pressure gas jets, you lose all the deposits and you eliminate the crevice corrosion completely. So maintenance is the trick for taking care of the crevice corrosion which comes because of the presence of deposits. And that is the same thing. So maintenance is very important. So next time if you're driving a vehicle or anything, even a bicycle, that mud guard and all this thing, one day you try to examine your bicycle. See inside, you'll see some deposit. Try to scratch it off. You will see under that the corrosion is happening. It's a very common observation. So here, if your paints are damaged, for example, then under the damage you can see there's a small gap in there. So if you lift that, you can see that whole area will start to corrode. quite faster. So damaged coatings can also lead to the crevice corrosion. Now this pictures was given by one of the student like you who was attending in 2009, and he took this picture from the toilet zone, and this was the kind of fitting that he observed in there. And once you remove this part here which I am marking by arrow, you see these two holes here. So inside the holes you are seeing that it's a brown color rust, so it's corroding. Outside it is painted, and if you see this part also on the side, the paint was damaged in this area, and you see this is a small view and this is a large view, and you'll see the red rust forming in here. And here is another fitting which you see this white tape being used, because this is a fitting in which you just screw it off, and the plumber used a white tape to seal the gap to minimize the crevice corrosion. So if you look at this situation number 1 here and situation number 2 here, 3 is already to close the gap. So what kind of corrosion you think is here in situation number 1, and what kind of corrosion you see is in the situation number 2 here? So take another 2 minutes. So once again, it's a part, and once you remove this part marked by the arrows, then you see these two holes here, and this is the pictures from the company toilet taken by this student in 2009, but it helps you in understanding the corrosion. So which type of corrosion you think is case number 1 showing here, and which type of corrosion is a case number 2 showing here? Are they the same type or they are the different type? Another 2 minutes, and then if you can figure it out, then we'll please raise the hand. So many of these questions are going to come in quiz 2, where you have to see something and you have to decide what you are seeing. So if I ask you what type of corrosion, you write the type of corrosion, that's good enough. Justification, 1 or 2 sentences, good enough already. That can fetch you 100% marks. All right, anyone can crack it? Which type of corrosion you can expect in case number 1? So let's start with the case number 1. Give a wild shot. You have only learned a few types of corrosion. Uniform corrosion, intergranular pitting, and crevice. That's all the choices you have so far to choose from. Anyone strong enough to tell me? Raise your hand. No one want to raise hand? The first case, yeah, please. Okay, let's go one by one. So case number 1 you feel is a crevice corrosion. What is your basis? Yeah, that's right. So we solved the case number 1. Now let's move to the case number 2, which is exposed to the outside environment. See, case number 1 is okay because once you remove that part, this is where the crevice can form. So this is correct. But once the part is in a fitted situation, you have this thing. Do you see any crevice outside here? No. If it is inside, always remember, that's a very valid query actually. Crevice corrosion takes place in crevice, not outside crevice. So always remember that. Crevice corrosion is always in the crevice, not outside. So in this case, it is in the crevice, not outside the crevice. No, only in here. All right. So we solved case number 1. Let's go to the case number 2. Yes. Okay, so you have a chrome plating here. So the chrome plating is no more here. So where is the gap formed? Because for the crevice corrosion, one of the conditions is to have a gap. Yeah, exactly. See, that's the question. If you have lost the coating, that area is exposed. It's a uniform corrosion, a material without a protection. So you have to first ask yourself, crevice corrosion happens because of the presence of crevice and presence of stagnant situation. It's a toilet. Toilets are normally not air conditioned. Humidity levels are quite high, right? So the water can always go in the gap and condense there. All right. So it's a kind of a stagnant situation, and inside the crevice it's going to corrode. But outside, the painting is damaged because the people are taking this part and putting back maybe a few times there. Painting is damaged. So wherever the painting is damaged, corrosion is happening. But now, can it fit in the crevice corrosion? No, because there's no gap. So it does not fulfill the criteria of crevice corrosion. So it's not a crevice corrosion, it's just a uniform corrosion happening all over the surface wherever the coating is damaged. All right. So you have to have a very clear mind. And of course, when you read the lecture notes, maybe you look at the video again, then it will strengthen your understanding even more. Now, another type of crevices are formed which are very commonly seen by the oil and gas industry, and especially where the liquids are transported beyond the ambient temperature, like oil fields in Alaska, right? So Alaska means like very low temperature. The liquid can freeze inside, so they have to be pumped at certain temperature. So for avoiding the heat loss from the pipe to the environment, you need insulation. And when you need insulation and the environment is wet and the insulation is not good, and over the time its quality deteriorate, then the water can seep in and there's no perfect bonding between the insulation and the pipe. Crevice corrosion sets in, and that is called as corrosion under insulation. One of the biggest failures in the Prudhoe Bay was because of corrosion under insulation. If you recall my first lecture, 180,000 tons of, or liters of, or barrels, I think it was barrels, 180,000 barrel production was affected per day basis. That was a lot. So that's a case of crevice corrosion also. So since we are in the crevice corrosion, we will also address this and then we'll stop today's lecture. There's something called the filiform corrosion, which is a special case of crevice corrosion also. And this kind of corrosion takes place under the coating. It's also known as under film corrosion or filamentary corrosion. So what you'll see from the top is something like a very fascinating structure like that, and which shows that it's a kind of a filiform corrosion. But it's a very specialized type of crevice, because between the coating, if the coating is not made properly, between the coating and the metal surface, you have a gap. And this gap again leads to a difference in the oxygen concentration, and the corrosion proceeds just along the coating and metal interface and form filaments like that. Something you can see here. This is not very clear and sharp picture, but these are the filaments being formed. You can see here filaments are being formed, and another here where it's a steel and you have the brown rust forming along the filament. So when you see this kind of appearance happening under the coating, then this is a filiform corrosion. Very special type of crevice corrosion. Now the humidity range again is 65 to 90%. That means it's a wet corrosion category. Unaffected below 65%. I told you that the range or the transition between dry and wet falls somewhere between 60 to 65%, and here is one more evidence that this type of corrosion takes place when the humidity levels are more than 65%. Below that it will not happen, and after and beyond that you will expect very big blisters, but not the filaments. So it's a very special case of crevice corrosion. So if you look at a magnified view of the mechanism, you see there's a breach here. So I will say breach of coating. That means the coating is damaged here, and then when the coating is damaged, you have the oxygen differential from this point to this point, and slowly the corrosion moves in this direction. So it has a head and it has a trail. Now the more deep you go from the breach, the less is the amount of oxygen compared to this location, and it is always a comparative difference. So the head will keep going in. And that's how it works. So some of the preventive measures to fight the filiform corrosion is you have to ensure that you polish your surface and you prepare your surface well. So whatever coating you are putting on that does not lead to any holidays or holes. So what is the meaning of holidays is this one, a discontinuity in the coating. That means the coating is not proper. Okay? Insufficient coating thickness, because that part is a weak part now. Presence of a crack, or the coating does not adhere properly. So this is what is the meaning of a holiday. And most of the polymer coating has pinholes and holes also. So that can also trigger the filiform corrosion. Lacquers and dry paints have to be avoided, and you should have the coating, if you can get a coating which is waterproof, that is excellent. Or you have the coating which are low water vapor transmission. That means they will not allow the water to go inside, or they are very resistant to that. So you can also go with the coating. And very interestingly, point number 5 is you can choose the brittle coatings. So how do you understand how the brittle coating works here is, if you go to the previous slide, you see that how the damage progresses from the breach, or you use a technical term now, holiday, some kind of improper part of the coating is a holiday. It's a technical term. So when it goes inside, this coating is pretty good. It's not cracking off. So if you use a brittle coating, for example, and this kind of corrosion sets in and wants to move, it will crack here. It will get damaged. So if it gets damaged, then oxygen will come from here. So when the oxygen comes in here, so oxygen concentration at head is equal to oxygen concentration at rail. So if there is no oxygen concentration difference, will the corrosion continue? Not really. Where it will form the cathodic reaction now. And that is why to fight the filiform corrosion, brittle coatings are also recommended. Understand? So initial 5 points, what makes an anode and what makes a cathode, you can still apply because that is the fundamental knowledge. Controlling anodic reaction or controlling cathodic reaction to control the corrosion is a fundamental knowledge. And you can apply that fundamental knowledge from wet corrosion to control any type of corrosion you want to. Any type of wet corrosion. All right, so I think that is where we will stop today. And we'll meet next week for the quiz. We'll only have quiz, so you may be a bit stressed, so I don't want to continue with the lecture after the quiz, so you can go and relax after that. All right? Any question? If possible, please see me with your questions and your lecture notes and your possible answer. If I can see where you are going wrong and where you are getting my concept wrong, I can correct you right at the root level. Email is other option, but I cannot explain as much in the email as I can explain face to face. All right? So we still have about a week to go. So please feel comfortable. And please return my attendance sheet. Whoever has it. Yeah, it is here, I think. No? You don't have it. So anyone who has my attendance sheet, please return it.